Long before the first telescope pierced the night sky, civilizations across the ancient world tilted their heads upward, tracing the paths of stars with nothing but their eyes and their boundless curiosity. Imagine standing beneath that vast, unpolluted darkness, where the Milky Way stretched like a river of light, and every flickering point told a story. For thousands of years, these early stargazers mapped the heavens, predicted eclipses, and tracked planets with nothing more than sticks, stones, and sheer brilliance. Yet today, their names have vanished from our textbooks, their achievements overshadowed by time. But here's the astonishing truth: without these forgotten pioneers, modern astronomy as we know it might not exist. Who were these hidden figures? Picture this: a Babylonian priestess carving celestial omens into clay tablets under the glow of an oil lamp, or a Greek philosopher calculating the Earth's circumference with nothing but a shadow and a hunch. These weren't just observers, they were detectives of the cosmos, solving mysteries that would take centuries to confirm. Some of their discoveries were so advanced, historians still debate how they pulled it off without the tools we rely on today. And yet, their stories have been buried under the dust of empires, their voices silenced by the passage of time. That's why this journey matters. Over the next 25 revelations, we'll resurrect these lost luminaries, the thinkers, the dreamers, the relentless seekers who laid the foundation for everything we understand about the universe. From the bustling streets of Alexandria to the quiet observatories of ancient China, their legacies whisper to us across millennia. So if you've ever looked up at the stars and felt that tug of wonder, you're already part of their story. Ready to meet the minds who turned the sky into their classroom? Let's begin. Aristarchus of Samos wasn't just ahead of his time, he was centuries ahead of the scientific consensus. In an era when most scholars believed Earth sat motionless at the center of creation, this 3rd century BC thinker from a tiny Greek island made an outrageous claim: the sun, not our planet, was the true center of the cosmos. Picture the audacity it took to suggest such a thing when even Aristotle himself taught that everything revolved around us. But Aristarchus didn't stop there. Using nothing but geometry, keen observation, and a mind unshackled by tradition, he calculated the relative distances to the sun and moon with shocking precision. His method was as elegant as it was ingenious. During a lunar eclipse, he realized the curved shadow Earth cast on the moon revealed our planet's true size. From there, he could triangulate the moon's distance. Then, by observing the angle between the sun and moon at first quarter phase, he estimated the sun was 19 times farther away than the moon, a figure we now know was off by a factor of 20, but still revolutionary for its time. Why didn't his heliocentric model catch on? The opposition wasn't just scientific, it was cultural. Ancient Greece revered Earth as sacred, the stable heart of creation. Philosophers like Cleans accused Aristarchus of impiety, arguing that displacing humanity from the cosmic center was an insult to the gods. Even Archimedes, while admiring his math, dismissed the sun-centered theory as absurd. But perhaps the most tragic twist, a single surviving manuscript of Aristarchus's work, quoted by Archimedes, is all that remains. The rest, his detailed arguments, his celestial diagrams, were lost when the Library of Alexandria burned. For 1700 years, his ideas lay dormant until Copernicus, unaware of his Greek predecessor, independently reached the same conclusion. History might have unfolded differently had Aristarchus's voice not been silenced by flames and dogma. Yet in that fragile thread of preserved knowledge, we glimpse a mind so bold, it saw the truth long before the world was ready to hear it. Hypatia of Alexandria wasn't just a scholar, she was a beacon of brilliance in a world that often dimmed the light of women's intellect. In the 4th century CE, while most women were excluded from academic circles, Hypatia strode into the lecture halls of Alexandria's legendary Mausian, her voice cutting through the murmurs of skepticism. She didn't just study the stars, she rewrote how her contemporaries understood them. With a mind sharp enough to dissect complex geometry and a passion for the cosmos, she crafted precise star charts that guided sailors and astronomers alike. Her work on celestial mechanics wasn't merely theoretical. She refined the design of the astrolabe, a handheld device that mapped the heavens with astonishing accuracy. Imagine holding that brass instrument under the Mediterranean sky, aligning its dials with the same stars Hypatia herself had catalogued centuries ago. But her genius extended beyond astronomy. Hypatia shattered expectations by excelling in mathematics, philosophy, and even engineering. Students flocked to her lectures not because she was a novelty, but because her insights were unmatched. She dissected the works of Ptolemy and Plato, challenging and expanding their ideas with a fearless intellect. In a society where women were often confined to the shadows, Hypatia commanded respect in the vibrant, male-dominated world of academia. Her very presence was a quiet revolution, proof that curiosity and brilliance knew no gender. Yet her story takes a heartbreaking turn. Alexandria, once a melting pot of ideas, became a battleground for religious and political tensions. Hypatia, a pagan in a Christianizing empire, found herself caught in the crossfire. Rumors painted her as a disruptor, a symbol of the old world resisting change. Then, in 415, an angry mob dragged her from her chariot, stripping away not just her life, but also countless manuscripts and discoveries lost to history. The details of her murder are gruesome, but what's even more devastating is the silence that followed. For centuries, her legacy was buried under layers of myth and deliberate omission. Why does Hypatia's story resonate so deeply today? Because it's more than a tale of scientific achievement. It's a reminder of how easily knowledge can be erased when prejudice outweighs progress. Her death marked the beginning of the end for Alexandria's intellectual golden age. But here's the twist: though her writings were burned, her influence wasn't so easily extinguished. Medieval scholars, whether they knew her name or not, built upon the foundations she helped lay. And now, as we piece together fragments of her work, we uncover a truth as bright as the stars she studied. Hypatia's legacy isn't confined to the past. It's a torch passed forward, illuminating the path for every thinker who dares to question, explore, and reach for the heavens, no matter who tries to silence them. Metonic of Athens peered up at the night sky in the 5th century BC with a problem to solve, one that had baffled scholars for generations. The moon's cycles didn't neatly align with the sun's journey across the seasons, throwing festivals and harvests into chaos. Imagine planning a celebration tied to the spring equinox, only for it to drift into summer over the years. But Meton, with the precision of a mathematician and the patience of a stargazer, spotted a pattern hidden in plain sight. 19 solar years almost perfectly matched 235 lunar months. This cosmic coincidence, now called the Metonic cycle, became the key to harmonizing heaven and earth. His breakthrough wasn't just academic, it reshaped daily life in ancient Greece. By engraving his calculations onto public stone tablets in Athens, Meton gave farmers a reliable way to predict planting seasons and priests a sacred rhythm for rituals. The cycle's elegance lay in its simplicity. After 19 years, the moon's phases returned to the same dates in the solar calendar. Picture the relief of a village elder no longer arguing over whether the festival of Dionysus was too early this year. The system was so accurate, traces of it still linger in modern astronomy, from the Hebrew calendar's leap months to the Christian calculation of Easter. What's often overlooked is how Meton's work bridged science and spirituality. Greek festivals weren't mere parties, they were acts of devotion, tied to celestial events believed to carry divine messages. A misaligned calendar risked offending the gods themselves. Meton's genius wasn't just in the math, it was in recognizing that the cosmos operated on a grand, repeating score, and humanity needed only to learn its rhythm. Yet for all its influence, his name rarely appears alongside giants like Ptolemy or Copernicus, perhaps because his innovation wasn't about grand theories of the universe, but something more immediate, giving ordinary people the power to sync their lives with the skies. The cruel irony, while we still use his cycle, the man himself faded into obscurity. No complete writings of Meton survive, and even his famous stone tablet vanished long ago. But next time you glance at a calendar or mark a holiday tied to the moon's phases, remember, it's the quiet legacy of an Athenian who taught us to dance to the cosmos's silent metronome. Eudoxus of Cnidus gazed at the stars in the 4th century BC and saw a puzzle that defied simple explanation. How did the planets dance across the night sky in their looping, unpredictable paths? While others shrugged at the celestial mystery, this mathematician-turned-astronomer devised a theory so elegant it would shape cosmic thinking for generations, a universe built from nested, rotating spheres. Picture 27 transparent shells, each tilted at precise angles, carrying the sun, moon, and planets in their eternal rotations. This was the heliocentric sphere model, where every celestial body moved not through empty space, but along the invisible gears of an intricate cosmic machine. Eudoxus' genius lay in his refusal to accept patchwork solutions. Earlier astronomers had struggled to explain retrograde motion, those moments when Mars appears to halt, reverse course, then resume its journey. His answer, multiple spheres per planet, each contributing its own motion like interlocking wheels. Venus might need 4 spheres, Saturn another 4, all turning in harmony to recreate the sky's complex ballet. It wasn't perfect, the math couldn't quite account for changing planetary brightness, but for an era without telescopes, it was a breathtaking leap. Enter Callippus, a sharp-eyed successor who spotted the cracks in Eudoxus' masterpiece. A century later, this Cyzicus-born thinker took the sphere count from 27 to 34, adding layers to explain subtle variations the original model missed. Where Eudoxus had grouped the fixed stars on a single outermost shell, Callippus gifted them their own set of rotating spheres, fine-tuning the celestial rhythm. His adjustments weren't just tinkering, they were acts of reverence, preserving the core idea while acknowledging the universe's stubborn complexity. Together, their work became the bedrock of Aristotelian cosmology. Aristotle himself adopted and adapted their spheres, though with a critical twist he transformed Eudoxus' mathematical abstractions into physical, crystalline layers that literally carried the heavens. It's ironic that while Aristotle's version dominated medieval thought, the original architects' names faded. Eudoxus and Callippus had never claimed their spheres were real objects. They were calculating tools, a brilliant workaround for an unsolved problem. What makes their collaboration so remarkable is how it embodies science's true spirit, building knowledge layer by layer. Eudoxus laid the foundation, Callippus reinforced it, and though both models were eventually supplanted by Kepler's ellipses, their legacy endures in how we approach cosmic mysteries today. They remind us that even wrong theories can light the way forward, provided they're crafted with enough curiosity and rigor to inspire those who come next. Timocharis of Alexandria worked in the shadows of history's greatest library, turning its rooftops into an open-air observatory where stars whispered secrets across 3 centuries BC. While names like Hypatia and Ptolemy dominate the story of ancient astronomy, it was Timocharis' meticulous records that gave them a foundation to build upon. Night after night, he mapped the positions of stars with nothing more than a simple sighting instrument called a dioptra, a far cry from today's telescopes, yet astonishingly precise for its time. His greatest gift to posterity, a detailed catalogue of stellar coordinates, the first known attempt in the Western world to systematically document the heavens. But his real breakthrough came when he noticed something peculiar. The moon occasionally passed directly in front of certain bright stars, blotting them out momentarily. These lunar occultations weren't just celestial coincidences, they were clues. By tracking these events, Timacaris unlocked a way to measure the moon's shifting path with unprecedented accuracy. Picture him hunched over clay tablets, etching timestamps as Spica or Aldebaran winked out behind the lunar disk. Each observation was a puzzle piece, revealing subtle irregularities in the moon's orbit that would later baffle and inspire Hypatia. Without these records, Hypatia might never have discovered precession, the slow wobble of Earth's axis that gradually shifts the stars' positions over millennia. It's a haunting thought. One man's forgotten notebooks became the Rosetta Stone for decoding cosmic motion. Timacaris' legacy is tangled with the Library of Alexandria itself, that beacon of ancient knowledge where astronomers, poets, and mathematicians collided. He wasn't just an observer, he was part of a collaborative machine, sharing data across generations. His work embodied the library's ethos, knowledge as a collective endeavor, each contributor a link in an unbroken chain. Yet history is cruel to middlemen. While Hypatia gets credit for connecting the dots, Timacaris' name survives only in scattered references, a ghost haunting the footnotes of greater discoveries. What makes his story so poignant is the fragility of progress. The same library that preserved his findings also doomed them to oblivion when its halls burned. We'll never know how much more he documented, how many star maps or theories vanished in the smoke. But here's the twist, even the fragments that survived reshaped astronomy. Timacaris reminds us that science isn't just about lone geniuses having eureka moments. It's about countless quiet observers who hand off their torches, trusting others to carry the light further than they ever could. Canon of Samos moved through the courts of ancient Alexandria not just as an astronomer, but as a storyteller of the stars. In the 3rd century BCE, while others tracked planetary motions or calculated Earth size, Canon turned his gaze to a seemingly empty patch of sky near Leo, a place where most saw nothing but darkness. But when Queen Berenice II sacrificed her legendary heir to ensure her husband's safe return from war, Canon spotted something extraordinary, a delicate cluster of stars that hadn't been there before. With a courtier's flair, he declared the gods had placed the queen's locks among the constellations, immortalizing her devotion as Coma Berenice's hair. It was a masterstroke of politics and poetry wrapped in celestial observation, blending myth with meticulous record-keeping. His friendship with Archimedes reveals another side of this forgotten genius. Their letters crackle with intellectual camaraderie, from shared geometric puzzles to debates about eclipse predictions. Archimedes once credited Canon with solving a complex problem about the area of a spiral, a theorem so elegant it later appeared in Archimedes' own works. Their collaboration wasn't just about exchanging ideas, it was a meeting of minds across disciplines where astronomy intersected with mathematics and engineering. Canon's eclipse studies, though less celebrated than his constellation myth-making, were groundbreaking. He documented the moon's phases with a precision that allowed him to forecast solar eclipses years in advance, a skill that would later inform Ptolemy's models. Yet history has a way of flattening such multidimensional figures. As later astronomers refined celestial mechanics, Canon's contributions were reduced to footnotes, his constellation treated as a charming myth rather than a scientific act of stellar cartography. His eclipse work absorbed into others' theories without attribution. Even Coma Berenice's, that shimmering tribute to a queen's sacrifice, was nearly erased when Ptolemy omitted it from his star catalogue. Only the keen eyes of Renaissance astronomers like Tycho Brahe rediscovered its faint glow, proving Canon's original observation had been right all along. What endures is the lesson his life offers. Science and storytelling need not be rivals. Canon understood that to make the heavens meaningful, one had to connect them to human experience. His legacy lives on every time someone points to that faint smudge of stars and recounts the tale of a queen's hair, suspended between myth and mathematics, waiting for the right observer to give it a name. Agrippa of Alexandria worked under the star-strewn skies of the 1st century, not with grand theories about the universe's structure, but with something far more practical, a celestial globe. This wasn't just a decorative object, it was a working model of the heavens, meticulously calibrated to mirror the actual positions of stars and constellations. Picture a bronze sphere etched with precise markings, its surface a mirror of the night sky, rotating smoothly on an axis to demonstrate celestial motion. Agrippa's genius lay in his attention to detail. He didn't just approximate star placements. He corrected earlier Greek models by incorporating fresh observations, adjusting for shifts in stellar positions that others had overlooked. His globe became a bridge between abstract astronomy and tangible navigation, a tool that could teach students, guide sailors, and even predict celestial events. Menelaus of Alexandria, working a few decades later, took a radically different approach. While Agrippa mapped the heavens in 3 dimensions, Menelaus dissected them with mathematics. His groundbreaking work, the Spherica, laid the foundation for spherical trigonometry, a branch of math crucial for calculating angles and distances on curved surfaces like the dome of the sky. Before Menelaus, astronomers struggled to describe the motion of stars and planets across the celestial sphere with precision. His theorems, like the famous Menelaus's theorem, provided the tools to solve complex problems involving arcs and angles, turning celestial mechanics into a solvable puzzle. Imagine trying to chart the path of a planet without these principles. It would be like building a house without a ruler or protractor. What's fascinating is how these two thinkers complemented each other. Agrippa's globe gave astronomers a physical representation of the cosmos, while Menelaus's math gave them the language to describe its behavior. One was a cartographer of the stars, the other an architect of their geometry. Together, their work formed a scaffold for later astronomers like Ptolemy, who would combine observational records with mathematical rigor to create the Almagest, the definitive astronomical text of antiquity. Yet history hasn't been kind to their legacies. Agrippa's globe, like so many artifacts of ancient science, was lost to time, surviving only in descriptions by later scholars. Menelaus's Spherica narrowly escaped oblivion, preserved through Arabic translations before trickling back into medieval Europe. Their stories remind us that progress in astronomy has never been a straight line. It's a tapestry woven from countless threads, some frayed, some forgotten, but all essential to the grand design. Agrippa and Menelaus may not be household names, but every time a modern astronomer calculates the trajectory of a comet or maps the curvature of spacetime, they're standing on the shoulders of these Alexandrian giants. Theon of Smyrna saw the universe not as a cold, mechanical void, but as a grand symphony, each planet humming its own distinct pitch as it circled Earth in divine harmony. In the 2nd century, while most astronomers focused solely on predicting celestial motions, this Greek polymath dared to ask why the cosmos moved the way it did. His surviving work, Mathematics Useful for Understanding Plato, reveals a mind straddling 2 worlds, the rigorous geometry of planetary orbits and the mystical Pythagorean belief that numbers governed reality. Picture Theon crouched over wax tablets, sketching the intervals between planetary orbits like musical notes, Venus a perfect fourth from the Sun, Saturn a haunting octave lower. To him, these weren't arbitrary distances, they were the very ratios that structured Plato's Music of the Spheres, an audible expression of cosmic order that human ears had merely forgotten how to hear. What set Theon apart was his refusal to divorce calculation from contemplation. While contemporary star catalogues listed positions and magnitudes, his writings explored how planetary speeds created harmonic relationships, much like strings of different lengths on a lyre. He documented Mercury's swift dance as a high, staccato pitch compared to Jupiter's deep, resonant glide, a concept later echoed by Kepler's celestial harmonies. Yet Theon's melodies weren't pure fantasy, they emerged from meticulous observation. He corrected earlier estimates of lunar phases, proving even mystics needed empirical grounding. His hybrid approach made him a bridge between eras, too mathematical for hardline mystics, too philosophical for strict astronomers, but invaluable to those seeking unity between the seen and unseen. Neoplatonists like Proclus would later seize upon Theon's ideas, weaving them into their vision of a universe emanating from divine intellect. But here's the twist: Theon himself never claimed to have all the answers. His work reads as an invitation, not a manifesto. Scattered among his geometric proofs are questions about why certain numbers recur in nature, why planetary intervals mirror musical scales, and whether these patterns hint at some deeper truth. He didn't just blend science and spirituality, he showed they could interrogate each other, each refining the other's rough edges. The tragedy: most of his original texts burned with Constantinople's libraries, surviving only in fragments quoted by later scholars. Yet even those shards shimmer with insight. When Renaissance thinkers like Ficino revived Platonism, they unknowingly echoed Theon's conviction that mathematics was the language linking stars to souls. Today, as physicists ponder whether the universe truly vibrates with hidden frequencies, we're still chasing the harmony Theon heard 2,000 years ago, not with lyres and intuition, but with quantum equations and space telescopes. His legacy whispers that perhaps the ancients weren't entirely wrong, just listening for the music in ways we're only beginning to understand. Cleostratus of Tenedos stood on the windswept shores of his Aegean island homeland, charting the heavens at a pivotal moment in history, the 6th century BC, when Greek astronomy was just beginning to emerge from the shadow of myth. While later figures like Hypatia would refine celestial mechanics, Cleostratus played a far rawer yet equally vital role. He was among the first Greeks to systematically track the sun's path through the constellations we now call the zodiac. With no telescopes or precise instruments, he relied on horizon markers and seasonal shifts, noting how the sun's position at dawn slowly migrated from Taurus to Gemini to Cancer over the course of a year. These observations weren't just academic, they became the backbone of his most enduring contribution, a lunisolar calendar that harmonized the moon's phases with the solar year, ensuring festivals aligned with both celestial rhythms and agricultural cycles. The controversy surrounding Cleostratus lies in the origins of his knowledge. Some ancient sources hint he may have encountered Babylonian star charts during travels to the Near East, where astronomers had already mapped the zodiac with astonishing precision centuries earlier. A few fragmented texts even credit him with introducing the 8-year calendrical cycle known as the octeteris, a system the Babylonians had used to reconcile lunar and solar dates. But here's where history gets murky. Did Cleostratus adapt these ideas independently, or was he a conduit for cross-cultural exchange? The debate speaks to a larger tension in the history of science: how much innovation springs from isolated genius and how much is borrowed, reshaped, and repurposed from earlier traditions. What's undeniable is the practicality of his work. Greek city-states had long struggled with chaotic, localized calendars where months drifted out of sync with seasons, leaving farmers unsure when to plant and religious officials arguing over festival dates. Cleostratus' system offered a solution by inserting extra months at precise intervals. To keep lunar months aligned with solar years, picture a farmer on Tenedos consulting Cleostratus' calendar etched on a stone stele, knowing the harvest festival would now reliably fall when the Pleiades cluster dipped below the horizon at dusk. His methods weren't perfect. The octeteris still accumulated errors over decades, but they laid groundwork for Meton's more refined 19-year cycle centuries later. The irony: Cleostratus' name survives not through his own writings, which vanished like so much of early Greek science, but through scattered references in later astronomers' critiques. Even his zodiacal observations were eventually overshadowed by Eudoxus' more sophisticated sphere models. Yet his legacy lingers in the very way we conceptualize time's passage, not as random or divine whim, but as a measurable, predictable dance between Earth, Moon, and Sun. Whether he was Greece's first cosmic synthesizer or an original thinker who arrived at similar conclusions as his Babylonian counterparts, Cleostratus remains a shadowy figure who helped turn stargazing from folklore into a science. Autolycus of Pitane peered at the horizon where the Aegean Sea met the sky, watching as stars emerged and vanished with mathematical precision. In the 4th century BCE, while other astronomers pondered grand cosmic theories, this quiet scholar from Asia Minor focused on something seemingly mundane: the predictable ways celestial bodies rose and set at the edges of Earth's curve. His surviving treatise on the moving sphere might sound dry to modern ears, but it's a revelation, the oldest complete Greek astronomical text we possess, a window into how early thinkers unraveled the mechanics of the heavens. Unlike the fragmented works of his predecessors, Autolycus' manuscript survived nearly intact, offering a masterclass in applied spherical geometry. He didn't just describe phenomena, he proved them with relentless logic, demonstrating why stars appear to accelerate as they near the horizon or how the moon's path shifts seasonally. What makes Autolycus' approach so groundbreaking is its stripped-down practicality. While contemporaries like Eudoxus built elaborate sphere models, Autolycus distilled astronomy to its observational essence: the geometry of a rotating celestial sphere as seen from Earth's surface. Picture a sailor on the coast of Pitane, using Autolycus' rules to predict when the bright star Arcturus would first become visible after sunset in autumn. His calculations weren't abstract, they were tools for navigation, agriculture, and timekeeping. He proved, for instance, that two observers at different latitudes would see the same star rise at different times, a foundational insight for later geodesy. His work on always visible and never visible star zones, regions of the sky that either never dip below the horizon or never rise above it depending on one's location, revealed Earth's spherical shape centuries before Eratosthenes measured its circumference. The elegance of On the Moving Sphere lies in its structure. Autolycus builds knowledge layer by layer, starting with simple definitions: what is a great circle on a sphere, before progressing to complex proofs about the angles at which celestial objects intersect the horizon. His theorem on how identical star rise/set patterns repeat at opposite solstices reads like a geometric detective story, each step meticulously reasoned. This wasn't just theorizing, it was a training manual for future astronomers. Hypsicles, who later refined zodiacal measurements, likely studied Autolycus' methods, and traces of his influence appear in Ptolemy's work on planetary risings. Yet history nearly erased his contributions. Unlike flashier discoveries, Autolycus' focus on fundamentals meant later scholars often absorbed his ideas without citation, treating them as common knowledge rather than revolutionary breakthroughs. Even his name was overshadowed by Euclid, whose elements borrowed from Autolycus' geometric techniques without attribution. The survival of On the Moving Sphere is something of a miracle, copied and recopied through Byzantine and Arabic traditions before resurfacing in Renaissance Europe. Today, as astronomers use spherical geometry to map exoplanet transits or calibrate space telescopes, they're unwitting heirs to Autolycus' legacy. His treatise reminds us that before humanity could grasp the universe's vastness, it first had to master the simple art of watching stars disappear over the edge of the world. Aratus of Soli didn't just study the stars, he sang them into the cultural consciousness of antiquity. In the 3rd century BCE, when most astronomical knowledge was locked behind dense technical treatises, this Greek poet crafted a masterpiece that made the cosmos accessible to anyone with ears to hear: the phenomena. Imagine a world without star charts or planetarium apps, where sailors, farmers, and philosophers alike relied on oral traditions to navigate both sea and season. Aratus took the dry observations of astronomers like Eudoxus and spun them into vivid hexameter verse, transforming constellations into characters and celestial motions into gripping narratives. His opening line set the tone: "From Zeus we lead forth the song, blending divine reverence with scientific observation in a way that captivated audiences from Athens to Rome. What made the phenomena revolutionary wasn't just its poetic flair, it was its dual role as both entertainment and practical guide. Aratus wove together two seemingly incompatible threads: the precise positional astronomy of Eudoxus's star catalogue and the rich tapestry of Greek myth. Orion didn't merely appear as a cluster of stars, he strode across the heavens with his belt glittering, a hunter eternally frozen in pursuit of the Pleiades. The Great Bear became not just a navigational marker but Callisto, the nymph transformed by Zeus's jealous wife, her tail stars dripping like amber tears. This wasn't simplification, it was alchemy turning data into something visceral. Farmers memorized his verses to predict planting seasons by the rising of Arcturus, while sailors chanted his descriptions of storm-warning constellations like the Hyades. Even in an age before printing presses, fragments of the phenomena have been found etched on pottery shards and temple walls, testament to its ubiquity. Yet beneath the lyrical surface lay razor-sharp accuracy. Aratus didn't invent the myths he retold, but he curated them with a scholar's eye, selecting variants that aligned with actual celestial patterns. His description of the zodiac's path, a slanting circle where the sun rolls through the 12 figures, mirrored Babylonian astronomy, while his warning that the moon's thin horns foretell winds from the north reflected generations of Mediterranean weather lore. The poem's climax wasn't a dramatic ode but a methodical list of weather signs tied to stellar phases, proving that beauty and utility could coexist. The phenomena's influence rippled far beyond Greece. Roman statesmen like Cicero and Germanicus Caesar competed to produce the finest Latin translations, treating Aratus' work as the ultimate intellectual flex. Centuries later, Byzantine monks would preserve it as a school text, and Renaissance scholars like Erasmus praised its fusion of art and science. Even today, when we call a sudden storm a tempest or describe someone's fate as written in the stars, we're unknowingly quoting Aratus' legacy. His genius lay in understanding that humans don't just need facts, we need stories that make those facts unforgettable. The night sky he celebrated wasn't a cold grid of coordinates, but a living epic where every star had a tale to tell, and every reader could find their place in the cosmos. Geminus of Rhodes stood at a crossroads of celestial knowledge, where Babylonian precision met Greek philosophical ambition. In the 1st century BCE, as Rome's influence spread across the Mediterranean, this astronomer penned a work that would become the ancient world's most enduring astronomy primer, the Introduction to the Phenomena. Unlike the dense, technical texts of his predecessors, Geminus crafted a lucid guidebook, a bridge between ivory tower theorists and practical stargazers. His genius lay in curation. He sifted through centuries of conflicting Babylonian eclipse records and Greek geometric models, distilling them into clear principles any educated reader could grasp. Picture a young student in Rhodes unrolling Geminus' manuscript, tracing his elegant diagrams of the zodiac's tilt or his step-by-step explanation of solar and lunar cycles. This wasn't just knowledge transfer, it was an act of intellectual democratization. What set Geminus apart was his fearless skepticism. Where others treated astronomical traditions as dogma, he subjected them to ruthless scrutiny. Take his dismantling of the vortex theory, a popular explanation for planetary motion claiming celestial bodies were swept along by cosmic whirlpools. Geminus didn't just reject it, he dissected its logical flaws with the precision of a surgeon. If Saturn moved slower than Jupiter because outer vortices rotated more sluggishly, he asked, why didn't this gradual speed change produce observable variations in planetary brightness or size? His critiques weren't destructive, they were constructive, pushing the field toward models grounded in observable evidence rather than poetic speculation. The introduction also reveals Geminus as history's first comparative astronomer. He didn't hide his debt to Babylonian eclipse tables, openly praising their empirical rigor while adapting their sexagesimal math for Greek audiences. Yet he also preserved uniquely Hellenic insights like Eudoxus' homocentric spheres, even while acknowledging their limitations. His work became a Rosetta Stone for celestial knowledge, showing how two great civilizations approached the same cosmic puzzles from different angles. Perhaps most strikingly, Geminus grappled with questions that still haunt astronomers today. In discussing calendar reforms, he highlighted a fundamental tension: should astronomy serve abstract truth or practical human needs? His compromised theoretical models adjusted for real-world utility echoes in modern debates about timekeeping standards and leap seconds. When he described how Egyptian astronomers ignored the moon's phases to create a purely solar calendar, he wasn't just recounting history, he was showcasing how cultural priorities shape scientific choices. The tragedy of Geminus is how much we've lost. His original manuscripts vanished, surviving only through later Byzantine and Arabic copies. Even his famous critique of astrology, where he reportedly distinguished genuine celestial mechanics from superstitious fortune-telling, exists only in fragments. But his legacy endures every time an astronomy textbook balances theory with observation, or when a scientist questions elegant but unproven assumptions. Geminus taught the ancient world that understanding the heavens required both reverence for data and courage to challenge tradition, a lesson as vital now as it was 2,000 years ago. Sosigenes of Alexandria walked into history with a paradox tucked under his arm: a sun so precisely measured, yet planets he utterly misunderstood. When Julius Caesar sought to untangle Rome's chaotic calendar in 46 BC, buckling under centuries of political tampering that left harvests falling in winter and taxes due under spring blossoms, it was this Greek astronomer he summoned. The problem was deceptively simple. Earth's journey around the sun didn't neatly match the moon's cycles, creating a mismatch that piled up 11 extra days each year. Sosigenes' solution: abandon lunar tracking altogether and anchor time to the solar year with ruthless precision. His calculations pegged it at 365¼ days, a figure so accurate it drifted by just one day every 128 years, forming the backbone of the Julian calendar that would govern Europe for 16 centuries. But here's where Sosigenes' story twists. The same man who pinned down the sun's rhythm with such finesse clung to celestial ideas that seem baffling today. In his lost work on the revolving spheres, he argued that Mercury and Venus didn't orbit the sun, but instead circled Earth in epicycles, their paths looping like drunken fireflies. Even more startling, he dismissed the idea of Earth's motion entirely, insisting our planet sat immobile at the universe's heart. How could someone so precise about solar years be so wrong about planetary dance? The answer lies in divided loyalties. Sosigenes wasn't just a scientist, he was a philosophical heir to Aristotle's geocentric cosmos, where Earth's centrality was theological dogma as much as science. His calendar reform worked because it relied on raw observational data, solstices recorded by Egyptian temple astronomers over generations. But for planetary motion, lacking telescopes to resolve Venus phases or Mercury's shifts, he defaulted to tradition's safety. The Julian calendar's implementation was anything but smooth. To realign Rome's timekeeping with the seasons, Sosigenes prescribed a staggering 445-day year of confusion in 46 BC, packed with intercalary months to reset the clock. Romans woke to find their markets shuttered for months long, Februarius Secundus, while tax collectors scrambled to adjust deadlines, yet the chaos birthed order. Sosigenes introduced the leap day, that extra 24th of February slipping in every 4 years, a stroke of brilliance so enduring, its skeleton survives in our modern Gregorian system. What makes Sosigenes' legacy so poignant is its duality. He gifted civilization a timekeeping tool of astonishing longevity while his cosmic world crumbled under later scrutiny. Ptolemy would refine his planetary errors into an elaborate but equally wrong system, while Copernicus and Kepler eventually dismantled the geocentric model entirely. Yet every time we mark a leap year or glance at a calendar, we're touching the work of an astronomer who, for all his blind spots, knew one thing unshakably: the heavens keep time with a rhythm worth chasing, even if humanity's steps occasionally falter in the dance. Dionysius Exiguus hunched over his parchment in 6th century Rome, wrestling with a problem far thornier than calendar math: the politics of time itself. Tasked by the Vatican to standardize Easter's shifting date, this Scythian monk faced a theological minefield. The existing system, counting years since Emperor Diocletian's reign, was untenable. Honoring a ruler who had persecuted Christians was unthinkable. So Dionysius crafted an elegant pivot. He reset history's clock to the birth of Christ, calculating what he believed was the year 532 since that sacred moment. His Anno Domini system wasn't just a dating convention. It was a quiet revolution, severing timekeeping from imperial vanity and anchoring it to faith. Yet irony tinges his legacy. While Dionysius got the concept right, his math was likely off by several years. Modern scholars suggest Jesus was probably born around 4 to 6 BC. Still, his framework became the invisible backbone of Western chronology, humming beneath every treaty, birthday, and history textbook. Across the Mediterranean centuries earlier, Anatolius of Laodicea tackled Easter's chaos from another angle. Where Dionysius focused on solar years, this 3rd century bishop mathematician refined the moon's role in determining the holiday. Borrowing from Babylonian and Jewish lunar calendars, he perfected a 19-year cycle where moon phases repeated almost exactly, a system so precise it corrected earlier errors that had Easter drifting into summer. Picture Anatolius in his library, comparing centuries of Alexandrian eclipse records to Hebrew Passover dates, spotting patterns others missed. His breakthrough wasn't just technical, it was diplomatic. By synchronizing Christian Easter with Jewish Passover's lunar timing while avoiding direct overlap, he bridged cultural divides in a fractured empire. What's startling is how these two thinkers, separated by 300 years, complemented each other. Dionysius gave Christianity a timeline divorced from pagan rulers, while Anatolius ensured its holy day resonated with celestial harmony. Both wrestled with the same paradox: how to yoke the erratic moon to the steadfast sun, creating a calendar that felt divinely ordained yet mathematically sound. Their solutions still echo today whenever a priest consults an ecclesiastical full moon table or a historian writes 2024. They're walking paths these scholars paved. The darker twist: neither man saw his work flourish in his lifetime. Anatolius' lunar tables were initially rejected by churches clinging to older methods, while Dionysius' AD system took centuries to catch on beyond monastic circles. Yet their persistence reveals a truth deeper than astronomy or theology. Time itself is a story we agree to tell, and sometimes the quietest reckonings reshape history's narrative most profoundly. Philolaus of Croton peered into the cosmos and saw not the earth but fire as the universe's beating heart. In 5th century BC Greece, where most philosophers still envisioned our planet as the unmoving center of creation, this Pythagorean radical proposed something astonishing: a universe orbiting a hidden, central flame he called the hearth of the cosmos. Picture a celestial dance unlike anything his contemporaries dared to imagine: Earth, Sun, Moon, and planets all circling this invisible inferno in concentric spheres, completing their revolutions every 24 hours. Even more startling, Philolaus claimed Earth itself rotated, presenting different faces to the cosmic fire as it moved. This wasn't just a tweak to existing models, it was a full-scale reimagining of reality, one that dared to dethrone Earth from its privileged position. What makes Philolaus' theory so tantalizing isn't just its audacity, but its eerie foreshadowing of later discoveries. While his central fire wasn't the sun, he placed that as just another orbiting body. The structural parallels to Copernicus' heliocentric model are impossible to ignore. Both systems rejected geocentrism, both required planets to move in circular paths around a focal point, and both challenged the intuitive notion that Earth stood still. Historians still spar over whether Copernicus encountered Philolaus' ideas during his studies of ancient Greek texts, or whether both thinkers arrived at similar conclusions independently. The evidence is cryptic. A handful of surviving fragments from Philolaus' book On Nature, quoted by later writers like Plato and Aristotle, often with disdain. One pivotal clue lies in a 16th century margin note in Copernicus' personal copy of a Pythagorean text, where he scribbled a reference to Philolaic motions, suggesting at least passing familiarity. But Philolaus' vision was more than a proto-Copernican sketch. It was steeped in Pythagorean mysticism. The number 10 held divine significance for his school, so he insisted the cosmos must have 10 bodies, hence his invention of a mysterious counter-Earth orbiting opposite our own, forever hidden from view by the central fire. This blending of numerology and astronomy baffled later scientists, yet it reveals a crucial truth. Ancient cosmology wasn't just about observation, but about seeking harmony between math, philosophy, and the sacred. When Philolaus described planets producing musical tones as they moved, a concept later echoed in Kepler's music of the spheres, he wasn't offering testable hypotheses but expressing a profound belief in a mathematically ordered universe. The backlash against his ideas was swift. Aristotle mocked the counter-Earth as absurd, while others dismissed the central fire as pure fantasy lacking observational support. Yet Philolaus' legacy endured in unexpected ways. His insistence that celestial motion required a non-Earth center planted a seed of doubt that would eventually bear fruit in the scientific revolution. Even his detractors couldn't unsee the questions he'd raised. If Earth wasn't special, what else might we have wrong about the cosmos? Today, as astronomers study exoplanets orbiting distant stars, we're still chasing Philolaus' fundamental insight that the universe refuses to revolve around human assumptions. His model may have been wrong in its details, but its spirit, the courage to reimagine reality from first principles, proved light years ahead of its time. Posidonius of Rhodes sailed the Mediterranean not just as a philosopher, but as a human measuring stick for the planet itself. In the 1st century BCE, while Rome consolidated its empire, this Greek polymath turned a simple voyage between Alexandria and Rhodes into one of antiquity's most daring experiments. Observing how the star Canopus barely grazed the horizon in Rhodes yet shone brightly over Egypt, he realized something revolutionary: Earth's curvature could be quantified. Using a dioptra, a precursor to the sextant, he calculated the angle between the star and the horizon at both locations, then extrapolated Earth's circumference to an astonishing 240,000 stadia. That figure, roughly equivalent to 29,000 modern miles, fell short of Eratosthenes' earlier and more accurate estimate, but Posidonius' method revealed something even more profound. By tying celestial observations to terrestrial geography, he proved the cosmos wasn't just above us, it was a ruler by which we could measure our own world. His brilliance didn't stop at geodesy. Posidonius also crafted the first systematic scale of stellar brightness, classifying stars into 6 magnitudes based on their visibility, a system still echoed in modern astronomy. Imagine him on a Rhodian rooftop squinting at the Lyra constellation, assigning Vega as his benchmark first magnitude star, while fainter stars like those in the Pleiades clustered into dimmer categories. This wasn't mere cataloging, it was an early attempt to quantify the heavens' intangible glow, bridging the gap between what the eye could see and what numbers could express. Yet Posidonius' most unexpected contribution wove the sky to the seas. His meteorological studies linked weather patterns to celestial cycles, arguing that lunar phases influenced tides, an idea dismissed as superstition until Galileo's era. He tracked how the dog star Sirius rising coincided with the Mediterranean summer storms, blending astronomy with practical forecasting. Sailors relying on his texts could suddenly predict squalls not as acts of Poseidon's whim, but as phenomena obeying cosmic rhythms. The irony, much like the stars he measured, Posidonius' legacy flickers in fragments. His original works perished with Rome's collapse, surviving only through quotes in Strabo's geographies and Seneca's essays. Even his Earth measurement was later mangled by Ptolemy, whose misinterpretation shrank the planet's size, a mistake that may have emboldened Columbus' fateful voyage. But in that fragile transmission, we glimpse a mind who saw no divide between earth and sky, number and myth. His true genius lay not in single discoveries, but in stitching them into a vision of nature as one vast, measurable tapestry, where every wave, wind, and wandering star told part of the same story. Seleucus of Seleucia stood alone in the 2nd century BCE, championing an idea that had been ridiculed for generations: Aristarchus' audacious claim that Earth revolved around the sun. While most scholars in Mesopotamia and Greece clung to the comforting geocentric model, this Chaldean astronomer from the bustling port city of Seleucia became heliocentrism's most vocal defender. His arguments weren't based on blind faith but on meticulous observation, particularly of the rhythmic rise and fall of the tides. Strolling along the Tigris River where it met the Persian Gulf, Seleucus noticed something revelatory. The tide's ebb and flow synced perfectly with the moon's position, whether it was looming large on the horizon or hidden from view. This wasn't mere coincidence, it was evidence of an invisible celestial hand tugging at Earth's waters, a force that made no sense if our planet sat motionless at the universe's core. What set Seleucus apart was his willingness to push Aristarchus' theory further with mathematical rigor. He reasoned that if Earth truly orbited the Sun, the Moon's gravitational pull would create tidal bulges, one on the side facing the Moon from its direct attraction, and another on the opposite side from Earth's own centrifugal force. His calculations suggested high tides should occur when the Moon was directly overhead or on the exact opposite side of the planet, a prediction that matched patterns fishermen and sailors had noted for centuries but never understood. Seleucus didn't have the physics of gravity as we know it, yet he intuited that the Moon's proximity and Earth's motion conspired to slosh the oceans like wine in a swaying chalice. The backlash was immediate. Established astronomers dismissed his ideas as fantastical, arguing that if Earth moved, wouldn't we feel its motion? Seleucus countered with an analogy still used in physics classrooms today. Imagine riding a smoothly gliding boat on a windless river. No rocking, no resistance, just the steady pull of the current. Would the fish beneath the surface sense the boat's movement? His critics scoffed, but Seleucus held firm, compiling tidal records from Indian Ocean traders and Mediterranean dockmasters to bolster his case. He even predicted that tidal ranges would vary based on coastal geography, with narrow inlets amplifying the effect, a phenomenon modern scientists now call tidal resonance. Tragically, Seleucus' original works vanished when the Library of Seleucia burned during Rome's invasions, leaving only fragments quoted by later skeptics like Strabo. Yet his legacy surges forward with every high tide. When Galileo revived heliocentrism centuries later, he cited tidal patterns as evidence where a Mesopotamian had beaten him to the insight. Today, as satellites measure the Moon's millimeter-scale tug on our oceans, we're still unraveling the forces Seleucus first dared to connect to a sun-centered cosmos. His story whispers an essential truth. Sometimes it takes a mind standing at the water's edge, watching the waves lick the shore with celestial precision, to challenge what the rest of the world believes is fixed and immovable. Hypatia of Alexandria turned the night sky into a mathematician's playground, where stars weren't just points of light but markers on an invisible grid. In the 2nd century BCE, while others marveled at the heavens, this scholar saw a problem to solve: how to quantify the celestial dance with precision. His answer came in the form of a groundbreaking text, the Anaphoricus, which didn't just describe the cosmos but mechanized it. Picture a series of concentric rings, each representing a planetary sphere, rotating at calculated speeds to replicate the motions of the sun, moon, and planets. This wasn't just theory, it was an early analog computer, a blueprint for devices like the Antikythera mechanism that would follow centuries later. Hypsical's spheres weren't passive models. They were dynamic tools designed to predict eclipses and planetary positions with a turn of the crank. What set Hypsicals apart was his obsession with standardization. Drawing from Babylonian astronomy, he made a decision that would echo through millennia, dividing the zodiac and, by extension, the entire celestial sphere into 360 degrees. Why that number? The choice wasn't arbitrary. The Babylonians' base 60 system lent itself to effortless subdivisions, allowing astronomers to split degrees into 60 minutes and minutes into 60 seconds. Hypsicals didn't invent this system, but he codified it for Greek science, transforming stargazing from qualitative observation into quantitative analysis. Imagine an Egyptian scribe or a Greek sailor suddenly equipped with a common language for celestial navigation, where the distance between stars could be measured as reliably as land surveyors mapped fields. The Anaphoricus itself was more than a treatise, it was a bridge between cultures. Hypsicals borrowed freely from Babylonian eclipse records and Egyptian calendar math, synthesizing them with Greek geometry into something greater than the sum of its parts. His calculations on the varying speeds of the sun across seasons, for instance, corrected earlier Athenian estimates by incorporating data from Mesopotamian clay tablets. Yet for all its innovation, the work nearly vanished. Only fragments survived the Library of Alexandria's decline, preserved by Arabic scholars who recognized its brilliance. Even Ptolemy, whose Almagest would dominate medieval astronomy, quietly absorbed Hypsical's degree system without fanfare, making it the invisible scaffold of celestial cartography. The irony: Hypsical's most enduring contribution feels so obvious today we forget it was ever revolutionary. Every time an astronaut checks a spacecraft's trajectory or a student measures angles in a protractor, they're using his 360-degree framework. His spheres may have been supplanted by Kepler's ellipses, but the language he gave the heavens, a language of precise, divisible arcs, still guides our eyes and instruments across the night sky. In a world where most scientific fame goes to those who discover new things, Hypsicals reminds us that sometimes the greatest breakthroughs come from those who teach us how to measure what's already there. Serapion of Antioch stalked the halls of his observatory with a singular obsession: numbers never lie. In the 2nd century BCE, when most astronomers still cloaked their celestial theories in philosophical musings, this Syrian scholar demanded something radical: hard evidence. While others spun intricate tales of crystalline spheres and divine harmonies to explain planetary motion, Serapion insisted on a simpler test: do the predictions match the sky? His critiques cut through the era's intellectual fog like a blade. Take the then-dominant Apollonian model of epicycles, where planets looped in perfect circles around imaginary points. Serapion scoured decades of Babylonian eclipse records, comparing them to Greek forecasts, and found discrepancies no amount of geometric elegance could explain. If the model cannot account for Mars' position next month, he reportedly argued, what use is its beauty? What made Serapion's approach revolutionary was his willingness to dismantle sacred cows. He openly challenged even Aristotle's assertion that celestial bodies must move in uniform circular motion, an idea treated as gospel for centuries. Pointing to Venus' erratic brightness changes, he argued that if the planet maintained a constant distance from Earth as uniform motion required, its glow shouldn't flicker so dramatically. This wasn't just nitpicking, it was early scientific skepticism in its purest form. Serapian's lost treatise on planetary irregularities allegedly compiled hundreds of such observational contradictions, creating a hit list for future astronomers to resolve. The tragedy: we know his work primarily through his detractors. Later commentators like Ptolemy dismissed Serapion as a mere calculator, more scribe than theorist, while Neoplatonists accused him of stripping the heavens of their divine order. Yet hidden in their criticisms lie clues to his influence. When Ptolemy grudgingly admitted in the Almagest that some planets required modified eccentricity to fit observations, he was tacitly conceding Serapion's point models must bend to reality, not the other way around. Even his nickname, the Babylonian, earned despite his Syrian roots, hints at his reliance on Mesopotamia's vast observational archives over Greek abstractions. One tantalizing fragment survives in a Byzantine manuscript. Serapion's claim that Mercury's orbit couldn't be circular because its speed varied unpredictably near the Sun. Centuries later, Kepler would prove him right with his laws of elliptical motion, unaware that an Antiochian outsider had sensed the truth long before. Serapion's legacy isn't in the theories he built, but in the questions he dared to ask, reminding us that progress begins when we let the stars speak for themselves, unfiltered by dogma or tradition. Achilles Tatius pressed his stylus into wax tablets under the flickering lamplight, sketching celestial mechanisms that defied the philosophical norms of 5th century Alexandria. While most astronomers of his era debated abstract theories of cosmic harmony, this enigmatic scholar approached the heavens like an engineer reverse engineering a divine machine. His surviving treatise on the configuration of the celestial spheres reads less like stargazer's poetry and more like an artisan's workshop manual, comparing planetary motions to the interlocking gears of water clocks and siege engines. Picture his radical vision. Saturn's slow march across the zodiac mirrored the largest wheel in a mill, while Mercury's skittish retrograde loops resembled a tiny escapement mechanism gone haywire. This wasn't just metaphor. Tatius insisted these mechanical parallels revealed the actual physics governing the stars. His most startling innovation was applying these principles to weather prediction. Unlike contemporaries who blamed storms on Zeus' whims or astrological omens, Tatius documented precise correlations between planetary alignments and Mediterranean wind patterns. When Mars and Jupiter converged in Capricorn, his records showed 80% of subsequent new moons brought gales to Rhodes. Such bold empiricism clashed with the era's intellectual currents. Neoplatonists dismissed his gear metaphors as vulgar reductionism, while Ptolemaic astronomers ignored his data because it contradicted their perfect spherical models. Even his supposed allies, the instrument makers crafting astrolabes and orreries, found his ideas too radical, clinging to traditional geometric designs rather than adopting his proposed mechanical modifications. The tragedy of Tatius lies in the fragments we've lost. Only 1/3 of his treatise survives, preserved not in Greek but through a 9th century Arabic translation discovered in a Cordoba library. What remains hints at even wilder theories: a claim that comets were not celestial portents but cosmic steam, released from overheating planetary mechanisms, and a detailed lunar model where craters resulted from impact strikes between invisible interlocking parts. Some scholars speculate these ideas were too uncomfortably close to atomism, a philosophy Christianity deemed heretical, explaining why later scribes may have deliberately allowed his work to crumble into oblivion. Yet traces of his influence linger unexpectedly. When Byzantine Emperor Constantine VII commissioned a golden planetarium in the 10th century, the engineer's notes referenced the Alexandrian artificer's principles of celestial gearwork. And in 1588, Tycho Brahe's assistant quietly borrowed Tatius' storm almanac methods to predict the winds that scattered the Spanish Armada. The ultimate irony: modern astrophysics increasingly describes the universe in mechanical terms: gravitational gears, cosmic clocks, orbital resonances, proving Tatius' intuition was millennia ahead of his tools. His peers couldn't hear the universes ticking over the noise of their philosophies, but today's radio telescopes might finally be tuning into the rhythm he alone dared to imagine. Theodosius of Bithynia wielded geometry like a sculptor's chisel, carving the heavens into perfect curves and angles. In the 1st century BCE, while Roman engineers paved roads across the known world, this quiet mathematician from northern Anatolia was mapping an invisible latticework, the fundamental rules governing spheres, not just as abstract shapes, but as the very fabric of the cosmos. His Spherix wasn't merely a textbook, it was a revelation distilling 300 years of Greek astronomy into 13 crystalline propositions that would become the scaffolding for medieval stargazers from Baghdad to Oxford. Picture a scholar in 9th century Damascus unrolling a parchment copy, tracing Theodosius' proofs with inked fingers. How to calculate the angle between celestial circles, why stars appear to rise and set at different times depending on latitude, or how to predict the sun's path across the zodiac without ever leaving the ground. What set Spherix apart was its ruthless elegance. Unlike Ptolemy's Almagest, which blended math with planetary theory, Theodosius focused purely on the geometry of spheres, the essential toolkit for anyone studying the sky. He proved, for instance, that all great circles on a sphere, like the celestial equator, bisect one another, a principle allowing astronomers to triangulate star positions. Another theorem demonstrated how the horizon always divides the sky into equal halves, regardless of where you stand on Earth, a counterintuitive idea if you've ever watched the sun seemingly rise unevenly over mountains. These weren't just academic exercises, they were the gears turning behind every astrolabe and armillary sphere. Theodosius' influence bloomed centuries after his death. Persian astronomers like Al-Farghani leaned heavily on Spherix to refine their own celestial models, while European translators in 12th century Toledo rendered it into Latin, where it became mandatory reading for Renaissance thinkers like Regiomontanus. Even Copernicus, in his De Revolutionibus, cited Theodosius' spherical theorems as the foundation for his own heliocentric calculations. The irony: Theodosius himself likely never intended his work to revolutionize astronomy. He saw it as an extension of Euclidean geometry, pure mathematics divorced from the messiness of actual stars. Yet by stripping celestial mechanics down to its bare geometric bones, he gave later astronomers a universal language to describe the sky's architecture. One particularly enduring idea was his treatment of parallel circles, lines of constant latitude on the celestial sphere. Theodosius proved these circles maintain fixed angles to the horizon, a concept that allowed Islamic scholars to standardize prayer times based on the sun's position. Picture a muezzin in medieval Cairo consulting a table derived from Spherix, knowing exactly when the sun's shadow would reach the length of his sandal to signal afternoon prayers. This fusion of abstract math and daily ritual epitomized Theodosius' quiet genius. His geometry didn't just explain the heavens, it synchronized human lives with their rhythms. The tragedy lies in what we've lost. The original Greek text of Spherix vanished, surviving only through Arabic and Latin copies. Even its author remains an enigma. No portraits, no anecdotes, just a name etched into the margins of history. Yet every time a modern astronomer calculates the trajectory of a satellite or maps the curvature of space-time, they're relying on the same spherical principles Theodosius codified 2,000 years ago. His legacy reminds us that sometimes the most revolutionary ideas aren't flashy breakthroughs, but the silent frameworks that make all future breakthroughs possible. Cleomenes of Alexandria stood in the shadow of giants, his ink-stained fingers preserving wisdom that might have otherwise crumbled into dust. In the 1st or 2nd century, when Rome's empire was at its peak, this relatively obscure astronomer penned a work that became an accidental time capsule on the circular motions of celestial bodies. At first glance, it seemed like just another textbook, a straightforward explanation of planetary motion and lunar cycles for students. but hidden within its pages were fragments of Posidonius' lost theories, quotes from Eratosthenes, and echoes of Hypatia's calculations. Cleomenes wasn't merely writing a primer, he was stitching together a patchwork of endangered knowledge, ensuring that future generations wouldn't lose the celestial insights of his predecessors. His treatment of lunar phases was a masterclass in clarity. While earlier philosophers like Anaxagoras had vaguely suggested the moon shone by reflected sunlight, Cleomenes laid out the mechanics with geometric precision. Picture a darkened lecture hall in Alexandria where he might have held up a bronze sphere to demonstrate. As the moon orbits Earth, sunlight strikes it from different angles, carving that familiar cycle from slender crescent to full silver disk. He didn't stop at mere description, he debunked misconceptions with the patience of a true educator. Some contemporaries argued the moon's phases resulted from its own shadow or even atmospheric interference. Cleomenes dismantled these ideas by pointing to the crisp, unblurred line between the moon's lit and dark portions, a detail only possible if the light came from a distant, singular source like the sun. Eclipses, however, were where Cleomenes' work truly shone. Drawing from Posidonius' lost writings, he detailed how lunar eclipses required perfect alignment, Earth positioned directly between sun and moon, casting its rounded shadow across the lunar surface. His description of solar eclipses was even more striking. He explained how the moon, though vastly smaller than the sun, could blot it out entirely because of its proximity to Earth. This wasn't just theory. He urged students to test it themselves by observing how a nearby coin could obscure a distant statue's face. Such hands-on analogies bridged the gap between abstract astronomy and lived experience, making celestial mechanics accessible to anyone willing to look up or hold up a coin. The bittersweet irony of Cleomenes' legacy is that he's often remembered not for his original ideas, but as a scribe who saved others. His meticulous citations of Posidonius' tidal theories and Eratosthenes' Earth measurements became the only surviving records of these breakthroughs after the Library of Alexandria's decline. Yet in that act of preservation, he performed a service arguably as vital as discovery itself. Think of it, without Cleomenes' diligent transcription, we might never have known Posidonius' groundbreaking work on stellar magnitudes or his methods for calculating Earth's curvature. The very fact that we can reconstruct ancient astronomy's evolution owes much to this unassuming scholar who believed knowledge was too precious to let vanish. What lingers most powerfully from On the Circular Motions isn't just its content, but its ethos. Cleomenes wrote not to dazzle peers with originality, but to illuminate, to pass the torch. His explanations of eclipses and moon phases still hold up today, not because he uncovered new laws, but because he honored old truths with such clarity that they became indelible. In a world where so much ancient science was lost to fire, war, and neglect, Cleomenes' quiet dedication to preservation reminds us that sometimes the most profound act of scholarship isn't to break new ground, but to keep the old ground from crumbling away. The flames that consumed the Library of Alexandria might have erased entire chapters of ancient astronomy, but whispers of these forgotten thinkers endured, carried on scraps of parchment, in the margins of copied manuscripts, and most crucially, in the minds of scholars who refused to let knowledge die. When Islamic empires rose in the 7th century, their astronomers didn't discard Greek science. They absorbed, refined, and amplified it. Picture a 9th century Baghdad scholar hunched over a crumbling Greek text, painstakingly translating Hypsical's zodiacal degrees or Theodosius' spherical theorems into Arabic, adding his own commentaries in the margins. The House of Wisdom, that legendary institution under Caliph al-Ma'mun, became a sanctuary for endangered ideas. There, thinkers like al-Farghani distilled Ptolemy's Almagest into accessible summaries, while al-Metonic corrected Aristarchus' solar distance calculations using sharper instruments. But buried in their footnotes lay something priceless: references to lost works by Timocharis, Serapion, and Seleucus, names otherwise erased by time. The transmission wasn't just passive preservation, it was creative reinvention. Persian polymath al-Sufi's Book of Fixed Stars didn't merely copy Greek constellations, it fused them with Bedouin star lore, preserving both traditions. In Cordoba, the astronomer Maslama al-Madriti adapted autolycus spherical geometry to calculate prayer times across Al-Andalus, proving ancient math could solve new problems. And crucially, these scholars acted as bridges. When Byzantine emperors like Constantine VII sought to recover classical knowledge, they turned not to Athens' ruins but to Arabic translations stored in Toledo's libraries. A 12th century monk might have gasped holding a Latin version of Menelaus Spherica, unaware it had traveled from Greek to Syriac to Arabic before returning to Europe dressed in Gothic script. Renaissance humanists completed the circle, but with a twist. When Regiomontanus printed the first European edition of Ptolemy in 1561, his preface hailed the Alexandrian as astronomy's sole genius, never mentioning the Islamic astronomers who'd kept Ptolemy's work alive for 7 centuries. Yet traces of the forgotten ones lingered. Copernicus' personal notes reveal he'd studied Arabic commentaries arguing against Ptolemy's equant model, sparking doubts that led to his heliocentric breakthrough. And tucked inside a Vatican manuscript, a bored scribe's doodle of concentric circles matches Philolaus' central fire diagram, proof that even the most radical ideas found clandestine passage. The real tragedy isn't just what was lost, but how close we came to losing everything. Without this fragile chain of scribes, translators, and marginalia writers, Hypsicles 360 degrees might have vanished with his Anaphoricus. Cleome's eclipse explanations could have dissolved into the Mediterranean mist. Yet these fragments, however scattered, remind us that scientific progress isn't a straight line. It's a labyrinth where dead ends sometimes hide the most vital clues. When modern astronomers peer into Philolaus' central fire and find the sun's nuclear furnace, or when oceanographers confirm Seleucus tidal theories with satellite data, they're not just validating ancient insights, they're stitching torn pages back into history's grand manuscript. The work of remembering, it turns out, is its own kind of science. Modern archaeology is peeling back layers of time with tools these ancient astronomers could never have imagined: LiDAR scans revealing buried observatories, multispectral imaging resurrecting faded star charts, and algorithms reassembling shattered celestial devices. One of the most startling reappraisals comes from the Antikythera mechanism, that bronze enigma salvaged from a 2,000-year-old shipwreck. For decades, historians dismissed it as an outlier too advanced for its era. But recent CT scans unveiled gears within gears, a miniaturized cosmos tracking not just lunar phases but eclipse cycles and planetary positions with jaw-dropping precision. The real shock, parallels to descriptions of lost devices by Hypatia and Geminus, suggest such mechanisms weren't rarities, but part of a broader tradition of mechanical astronomy we're only beginning to uncover. Digitally reconstructed star catalogues tell a similar story of overlooked sophistication. When researchers fed fragments of Timocurus' observations into planetarium software, they found his coordinates matched genuine stellar positions within 2 degrees, an accuracy achievable only through disciplined multi-generational record-keeping. Even more telling are clay tablets from Uruk, where Babylonian astronomers logged Venus movement centuries before the Greeks. Modern statistical analysis reveals these weren't random scribbles but meticulous data sets, with planetary positions calculated using zigzag functions, an early form of calculus predicting celestial speeds before Newton was born. Yet the reassessment isn't just about vindicating ancient accuracy, it's uncovering deliberate innovation where we'd assumed error. Take Ptolemy's much maligned star brightness scale. Historians long accused him of copying Hypatia's magnitudes without verification. But when astrophysicists recently modeled atmospheric conditions over ancient Alexandria, they discovered Ptolemy's rankings aligned perfectly with how stars would have appeared through the city's humid, dust-laden air. proof he'd recalibrated the system for local visibility. Even Aristarchus, off by a factor of 20 solar distance calculation, gets a second look. New research suggests he may have been measuring Earth's orbit ellipticity without the vocabulary to describe it, his error reflecting an incomplete, but not incorrect grasp of heliocentrism. The most poignant rediscoveries emerge from overlooked margins. A palimpsest in Istanbul's Topkapi Palace, scraped clean and reused for medieval prayers, was found to contain erased diagrams from Autolycus on the moving sphere. Spectral imaging resurrected his original proofs, showing how Renaissance scholars like Clavius had unknowingly replicated his spherical geometry centuries later. Meanwhile, AI pattern recognition applied to Chinese oracle bones revealed Shang dynasty eclipse records from 1600 BC, predating Greek astronomy by nearly a millennium, with descriptions so precise they've helped modern astronomers recalibrate Earth's rotational slowdown over millennia. These aren't just academic corrections, they're dismantling the myth of linear progress. When Seleucus' tidal theories resurfaced in Arabic commentaries, oceanographers realized his 2nd century BC model anticipated by 2,000 years our understanding of lunar nodal cycles' effect on extreme tides. Similarly, Hypatia's long-dismissed meteorological astrology now appears to have been an early attempt at linking solar activity to climate patterns, a connection space where the scientists only confirmed in the 1980s. What we once labeled superstition often turns out to be observation without adequate technology, intuition straining against the limits of its tools. The revolution isn't confined to libraries. Experimental archaeologists like Michael Wright have built working replicas of devices described by ancient texts, from Philolaus' central fire model, which, when constructed as a mechanical orrery, produces eerily accurate planetary transits, to Serapian's eclipse predictors. The results challenge assumptions. Many theoretical models function better as predictive instruments than we'd credited. A team at the University of Thessaloniki recently demonstrated that Theodosius' spherical geometry, when applied to Hellenistic sundials, corrects seasonal timekeeping errors to within 15 minutes precision, rivaling early medieval clocks. Perhaps the most humbling lesson lies in how these rediscoveries reframe collaboration across time. Digital reconstructions of the Library of Alexandria's layout suggest its famed daughter library at the Serapeum housed an astronomical workshop where scholars like Hypsicles and Menelaus might have literally passed tools between generations. Fragmentary star catalogues painstakingly reassembled from Oxyrhynchus papyri show incremental refinements over centuries, proof that ancient science, like modern research, advanced through peer review and iterative improvement. We're not just recovering lost knowledge, we're witnessing the resurrection of history's first scientific community, one that asked, tested, and transmitted ideas with a rigor we're only now learning to fully appreciate. These forgotten astronomers didn't just gaze at the stars, they rewrote humanity's place in the cosmos, one observation at a time. From Aristarchus' sun-centered daring to Hypatia's meticulous charts, their ideas were seeds planted in the thin soil of antiquity, surviving centuries of neglect to bloom in the minds of later thinkers. Imagine Copernicus reaching for the same truths as Seleucus, or Kepler hearing echoes of Philolaus's cosmic harmonies. Proof that progress isn't a straight line, but a scattered constellation of insights waiting to be connected across time. Every equation predicting a comet's path, every satellite measuring tidal forces, owes a debt to these pioneers who worked without telescopes or acclaim, armed only with sticks, shadows, and boundless curiosity. Yet for every name we've salvaged, Timocharis, Meton, Sosigenes, countless others have vanished into the dark. Picture the anonymous Babylonian who first noticed Venus's repeating cycle, or the Egyptian priestess who tracked Sirius's rising to predict Nile floods. Their tools may have been simple, but their legacies are etched into the fabric of modern science. The real wonder isn't just how much they got right, but how much they dared to question. When Theon of Smyrna heard music in planetary motion or Autolycus mapped the geometry of rising stars, they weren't just collecting data, they were teaching us how to see. So the next time you look up at the night sky, remember, you're standing on the shoulders of giants whose names history forgot. Their stories remind us that discovery isn't reserved for the famous or the well-funded sometimes. It begins with a single person tracing patterns in the dark, trusting that someone someday will follow their lead. Want to uncover more hidden threads in the tapestry of science? Join us as we keep digging, because the past still has secrets to share, and every subscription helps bring another lost genius into the light.